So this is a complementing lecture for section 1 on Friday's first class and section 2 for Wednesday's first class. So this is just a complementing lecture. So in our first week, what we did was, let me just highlight what we did on the first week. So in the first week we had a brief introduction, then we discussed about the open channel flow, a brief introduction to open channel flow, and we discussed about the classification, flow classification. There are various types of classification based on time as the criterion, based on space as the criterion, use of viscosity for the classification, and also we have discussed about the Froude's number. And then we discuss about the uniform flow velocity, where we discuss about the Jesus equation, which gives us the relation velocity for open flow. This velocity is an average velocity is equal to Jesus coefficient times root of hydraulic radius times the slope. So this was the equation that we derived last week. So in this week I'm going to let's discuss about the few other topics. So when it comes to second week, this is my lesson plan for the second week. We are going to have flip class. In the flip class, I want you to revise the first week's concept and prepare your individual notes. Okay, the material to be used to make these notes are already uploaded in your VLE. Please check in your VLE, and also please work in a group and analyze basic problems. So it is also available in your VLE. Please go and check it out, and I want you to work in group to analyze these problems. And materials, as I said, is already available in VLE. Next is we have to discuss on the concepts of specific energy. That is what we are going to do, and as well as we have to discuss the momentum principle. Okay, so for this class, let's discuss what specific energy means. Okay, so I'm going to start here. So let me write down the topic first. So it is the specific energy. Okay, so number 2 is specific energy. Okay, in an open channel, let me draw a reference diagram. In an open channel, when water is flowing like this, water is flowing in this direction. Okay, and let me also draw an arbitrary datum. When you talk about the specific energy, we are referring to a particular cross section. Let me say this is a cross section here. Okay, and before even we go into a specific energy, let's describe what total energy means, what energy in fact means. So as we have already studied, energy in flowing fluid comprises of the pressure energy, pressure plus the potential plus the kinetic energy. That's what we have discussed. Now when it comes to open channel, the pressure energy for open channel is simply the depth of flow. Okay, this is the hydrostatic pressure, and potential energy is what is the height of this cross section from the datum. So this is the Z, and the velocity, the kinetic energy, is described as the velocity squared by 2g. This is what's also known as velocity head. So the total energy at any cross section, let's say cross section A, total energy at any cross section A is given by the total energy is given by Z plus y plus v square by 2g. Now if we have to define this, then it is the energy per unit weight of water measured from a arbitrary datum or a reference point. So this is the definition of total energy. Now let's come back to our specific energy. So the specific energy is defined as energy per unit weight, energy per unit weight of water measured from the channel bottom. So here, if I again go back to my diagram, the specific energy is the energy per unit weight of a water measured from the channel bottom. Now instead of A, let me take another cross section. Let's say this is B, section B. So at this location, the specific energy is simply the depth and its velocity head. So specific energy here would be specific energy at B is equal to y plus v square by 2g. So again, come back here. So we have already defined the specific energy, that is energy per unit weight of water measured from the channel bottom. So mathematically, specific energy is equal to the depth of flow plus v square by 2g. So this is the specific energy. Okay, so let us give a in-depth treatment to this, what this specific energy is. So number one is, when we talk about specific energy, you need to be very clear that we are talking about about a point, about a cross section. You are talking about one particular section, energy at one particular section. So what we have to understand here is, if we take let me draw the same figure again. So if the water is flowing here and we are considering our section at A, and we are only interested to find the specific energy at this particular cross section. So similarly, if I just make the cross section of this is the longitudinal section. If I make the cross section, let's say this channel is the let's say it is a rectangular channel. So it's a rectangular channel. So if we have to plot specific energy, the graph for specific energy is going to look something like this. Okay, it's going to look something like this. So I'm going to make one line that is 45 degrees with the horizontal, and our specific energy is going to look something like this. Okay, so you can see this, the specific energy curve. So here this line represents y plus v square by 2g, and this is depth. So at different depth, let's say this is the specific energy. For specific energy at this depth corresponds to this value. Specific, if the depth was here, if the water was flowing at this depth, for example, then our specific energy is going to be something of this value, this magnitude. So when the depth changes, specific energy changes, and if you plot that, you are going to get a very smooth C type of curve. Now what we are interested is what and when there will be minimum specific energy, at what condition there will be minimum specific energy. So for that, what we do is, let's take the equation, a specific energy equation, that is specific energy is equal to y plus v square by 2g. Now we know that discharge is area times velocities, right? And in this exercise, what we are doing is, we are allowing the depth to vary, but we are simply keeping the discharge constant. So number one is discharge is constant, Q is constant. Please understand that same discharge can pass through this cross section at different depths. It is when depth changes, it not necessarily discharge has to change. Okay, so why and although the depth, and there's a relationship between the depth and the discharge, but for varying discharge, for a constant discharge there could be varying depth. Okay, so this is what you need to understand. What I mean to say is, when you pass same discharge, for let's say you are passing 1 meter cube per second, this 1 meter cube per second water can pass through this cross section at different height. So that is what I mean. So from this expression we know that V is going to be Q by A, and V square is going to be Q square by A square. So if I replace this in equation 1, our specific energy would be Y plus Q by A square times 1 by 2G. And now we want to find the condition when will there be minimum specific energy. So I believe you must have studied about maxima and minima. For that, what we do is we differentiate the specific energy and equate it to 0. So d of specific energy by dy is equal to 0. That is what we do to find out the condition for minimum specific energy. So let's differentiate this. So E0 is equal to, because I said when you differentiate we need to after differentiating we are equating it to 0. So when you differentiate y with respect to y, we are going to get 1, and when we differentiate this value with respect to y, what we're going to get. So here let me tell you that Q square by 2G is a constant, and A square 1 by A square is what we need to differentiate with y. So first thing what we are going to get is minus 2, and then 1 by A cube times dA by dy. What I have done is I differentiated d by dy of 1 by A square is equal to, this is what we are going to get, minus 2 by A cube dA by dy. This is what we are going to get. So this is what I have done here. So let's further simplify this. So 0 is equal to 1 plus, or else let us make it quite a little bit interesting. So I am going to push this negative sign this side, and I will get Q square by 2G. So 2 and 2 gone, and I'm putting this negative this side, so is going to become positive. So let me erase this 2. This 2 is going to go. So we are going to get Q square by G times 1 by A cube times dA by dy is equal to 1. So this is what we are going to get. This is the condition for the specific energy to be minimum. But now confusion comes, what is dy by dA? So if you just take any cross section, and water, let's say water is here, and if you take any small strip, this strip, let's say of the width dy, and let's say this is the top width t, and if you need to find the area of this top width, is going to be t times dy is going to be dA. So from here dA by dy is nothing, it's just the top width of a cross section. So from here we understand that dy by dA is the top width. So here we can replace this. So we are going to get Q square by G times 1 by A cube times T is equal to 1. In another word, what we can say is, let me segregate these terms. So Q square by G is equal to A cube by T. So this is the general condition for specific energy to be minimum. So if in any flow, if this condition is satisfied, then definitely the specific energy will be minimum. So specific energy is minimum. On the same note, what I want you to what I want you to try it on yourself is prove that, prove that this is your as a thought for the day. You can try it yourself. Okay, so prove that discharge is maximum when specific energy is minimum. Hint: now to solve this, you have to vary discharge, and discharge is not constant. To solve this problem, you should not consider discharge as constant. Don't consider discharge Q as constant. So this is the hint. If you don't consider Q as as constant, then definitely you can prove that discharge is maximum when specific energy is minimum. Okay, so this is what you can try for yourself. Okay, then with this we are good to go. So thank you.